So we've talked about what CDMA is. Now we're going to talk about the different types of codes. They are grouped into 3 categories. Orthogonal, these are the perfect ones, the Hadamard-Walsh, so each code has no effect on the other code. Semi-orthogonal, and we'll explain why we need semi-orthogonal, and these are known as gold codes. And then just a totally random code. So if we had a series of ones and minus ones with equiprobability of occurring, so it's a completely random code, so we will show, depending on our detector, then how effective random semi-orthogonal and orthogonal codes are compared to each other. You will do this in your laboratory exercise using MATLAB. So, first of all, the orthogonal code. This is known as the Hadamard-Walsh code. First of all, we have a 2x2 code. So we assign the 2x2 matrix. Then if we have 1, 1 on the first row and 1 on the second row, and finally have the inverse of 1, so -1 in the bottom right hand position, or column 1, row 1. It's highlighted here. So we could have the spreading gain would be 2, and the number of users would be 2. So if we then created a 4x4 matrix, what we would do is we would copy the contents of the 2x2 matrix to the uppermost elements. We would copy them down to the second and third row as shown, and also across the first line. And then in the bottom right hand corner, which is highlighted, we would reverse. So inverse, -1 where 1 was, and 1s where -1 are. So you'll see that the transpose and the original matrix of these are equal. Hence, when you multiply the two together, you get the identity matrix. You can try it if you like. So, in this case, for the 4x4 code, we would be able to have one user having this code, the second user having this code, the third user having that code, and the fourth user having that code. And the gain would be 4, and we could have 4 users. We could do this again for an 8x8 matrix, so we copy the entire 4x4 matrix up here, and we follow the same procedure, copying it there and copying it in the bottom left hand corner, and then this is the inverse. So this is the 8x8 matrix, so we could have a maximum of 8 users. Obviously we don't have to use all of the rows, but the spreading gain would be 8. The problem with this is we've got a fixed spreading gain. So for true orthogonality, for example, we couldn't give this as a spreading gain. If we gave the code here for a spreading gain of 4 for one user, those spreading gains are the same. So this is a subset of this. They're all subsets of each other, so these are not very practical. If we've only got a small number of users, then these are very secure. However, they're not practical. For this case, we use semi-orthogonal codes. So in a semi-orthogonal code, computers cannot generate random numbers, as you probably already know. So what we'll use is D-type flip-flops or a shift register. Here we have 4 stages in our shift register, very similar to how convolutional encoding is done. It's known as a PN generator or a pseudo-noise generator. And what pseudo-noise means is it is pretend noise. So it's pretend random. So it isn't really random, because after a certain period of time, that the output repeats itself. and the output repeats itself after 2 to the power of m minus 1, where m is the number of memory elements. So in this case, 2 to the power of m is 2 to the power of 4, take away 1, which is 15. The reason it's take away 1 is because you will be in a certain position and then this position will repeat itself. What do I mean by that? Okay, so I shall show you. So imagine the contents of each shift register are as shown here. So we have 0, 0, excuse me a second, 0, 0, 0, 1. The initial conditions, if everything is 0, then this won't work. So we need to have a NAND gate connected to all of these. In reality, a NAND gate to ensure that the 0, 0, 0 condition never occurs. And what happens is we choose certain outputs of the memory elements to feed back to the beginning. So there's no input here. The output is the feedback stages of whatever we choose. In this case, it's the output of 3 and 4. So the output in this case, I've chosen it to be 1. I could choose any configuration here. The result would still be the same. So we'll have these 0, 1, 1, 2 and 3 as 0 and 4 be 1. So here if we've got a 1 here and a 0 here, then the exclusive OR to that would be a 1. The truth table for exclusive OR, as I've said, is 0, 0, 0, 1, 1, 0, 1, 1. So for that it's 1 and those two it's 0. So 2 zeros is a 0, a 0, 1 or a 1, 0 is a 1, and a 1, 1 is a 0. We can have more than 2 inputs to an exclusive OR. If we remember the term, if there's an odd number of 1s, the output is 1. If there's an even number of 1s, the output is 0. Or 0, of course. So what we then do is we send this output 1 and 0. The output is 1. It gets fed back to position 1. Then everything shifts to the right one. So we have a 1 here, and then these 3 zeros are shifted 1, 2, 3, because this is what a shift register or a D-type flip-flop does. Again, I'm showing 1s and 0s here because these are generated by Boolean algebra. So 1s and 0s. Now we have a 0 here and a 0 here, so the output is going to be 0. So we're going to have 0, and then these are going to be shifted. So we've got 0, 1 here, 0, 0. Hence we have 0, 1, 0, 0. Then we have 2 zeros still on the input, so we have another 0. So the output's going to be, the next line is going to be 0, 0, 1, 0. Then now we have on the output to shift register 3, we have a 1. So the input here is going to be a 1. So we're going to have 1, 0, 0, 1 as the next line. And hence 1, 0, 0, 1. So we repeat the process over and over again until we come to a point where we notice that the contents of the shift registers match the contents of the shift registers. This is the point at where the sequence is complete. So this is my entire sequence of pseudo-noise sequence. This is the pseudo-noise code that's being output from this circuit. One user could be given this code. You'll notice that this code here, or you might notice that this code here, is time shifted by 1. So essentially every single output is a time shifted version of the other. So that's time shifted by 1, that's time shifted by 2. So that's 1 time shift, this is 2 and 3. So we've got 4 separate codes here, each time shifted by 1. If we try and correlate any of those 2 codes, they will show a low value. It won't be 0 because they're not truly orthogonal. They're only semi-orthogonal with one another because they're similar. They're just not in synchronization. So to make this more orthogonal, we can increase the number of stages, first of all. So in this case, we've got 4 stage, which is the same, a 6 stage and an 8 stage. So the length of the 6th stage, so the time before the code repeats itself, is 2 to the power of m, take away 1, 2 to the power of 6, take away 1, so it's much greater, and 2 to the power of 8 minus 1 for the third one. We can see that the outputs are the last one and the previous, on the penultimate one, take away 1. For the 8 stages, we have 4 feedback stages. Now, you have to look in literature because to get this optimal length code, it's not you can't just pick a random number of feedback stages. Only certain stages work. I mentioned gold code in the title, but we've not actually mentioned gold code yet because we're just talking about PN. So for the pseudo-noise, as I mentioned before, the trouble with the orthogonal is we had a fixed gain. With the pseudo-noise, we can choose the number of chips to represent the code, and it won't affect the semi-orthogonality. However, to make it orthogonal, in a gold code generator, what we do is we have 2 shift registers working in parallel, and then we exclusively OR the outputs of those 2 to provide the final output. So in this case, we've got a 1, 2, 3, 4. We've got 5 stages. So this repeats after 2 to the 5 minus 1. And another one, which also repeats after 2 to the 5 minus 1. But they're completely different. So when we combine the 2, we exclusively OR this one with this one. And we get the output. So this is how gold code sequences work. Don't really need to explain random because this is just totally random. I've already described it. Okay, so when we generate the code in MATLAB, what I've done here is got 3 examples. S, we choose S depending on which type of code we want. If you're simulating orthogonal, then we comment out these and this one. And vice versa, so you need to comment out each one. So we have the Hadamard function in MATLAB. So we just say what size we want the matrix, and then we are scaling down the output because it won't give us 1s and 0s. It'll give us the square root of n. What I meant to say is it doesn't give 1s and minus 1s. It gives the amplitude of square root of n. Then if we want to generate the gold code, then we would comment out these 2 lines and uncomment these by taking the percentage signs away. S1 and S2 are the generator matrices for the pseudo-noise shift registers. So the first input will be connected in the exclusive OR, and the third one, and then the first 3 and the last one are connected in the exclusive OR. You will be explained this in your laboratory sessions. The output is scaled down by 1 over the square root of the size of the number of codes n, and the HG is the cyclo function, which you can download from Blackboard, and we have the 2 S1s and S2s. The actual n in this case is defined by the number of taps that we have here on the pseudo-noise generator. So we have 1, 2, 3, 4, 5 in this case. Then the random code is just 1s and minus 1s, and we again sign them that we again scale them down, and we have k users, so we use the first 1 to k. So the output signal to noise ratio, if our input signal power is P for all users, The noise power is given by the variance, or sigma squared, which is the noise floor times the bandwidth of only the message, not the bandwidth of the spread code, so the narrow bandwidth. Then the effective interference power is given by P divided by the gain, or the spreading gain, which is also equal to the chip rate. The chip rate is essentially how much faster how many bits per chip that we have, so how many bits in the spreading code we have compared to one data bit. The total noise power is therefore the variance, or the sigma squared, plus P over G. So the interference power, or the multiple access interference, this is the power that is by other users transmitting on this network at the same frequencies. So then this is the MAI, or multiple access interference. So the signal to noise ratio at the output is given by P, the signal power, divided by the total noise. So this is the addition of the noise and the multiple access interference. So P over sigma squared plus P over G. So if we divide every single term by sigma squared, that gives me P squared, P over sigma squared over sigma squared, which cancels to 1, plus P over G sigma squared. P over sigma squared is the signal to noise ratio of the message. So we can further reduce this equation down to SNR of M divided by 1 plus SNR of M over spreading code, or G. We need to remember this for later use. So as I've already mentioned, at the receiver side we have our actual message times our spreading code, so message 1 times spreading code 1, plus message 2 times spreading code 2, all the way up message 3 times spreading code 3, all the way up to message K times code K, plus our noise. And we always have the receiver, so this would be D1 of T is RA1. So D, for instance, D2, so at user 2, D2 of T would be R times code 2. And DK would be R times AK. So code K times T. But for our user 1, the received signal D1 is M1 time, or approximately M1 times A1 times the other A1, because R is this, excuse me a second, is this times A1, every single term here, so it's also P2 times A1, so this would be P2 is the power of this, and PK A1, because we've only got A1 at the receiver, so we're not despreading message 2 because we don't have code 2. So what we receive is P2, so this is the wide spreaded multiple access interference from user 2. Here, PK, this is the widespread signal from user K. And then also the noise times the spreading code 1, and that is just the same as saying the noise. because we've shown that when we multiply a spreading code with nothing but noise, then we still get noise. So the signal is these two get rid of each other, plus we have some spreading gain. Then we have the second power P2 times A1 plus PK times A1, and we've shown previously in the previous slides that these are wideband interference plus the noise. So our signal it's much narrower now, and it has a high amplitude. So again, we always want to find the signal to noise ratio at the output so that we can predict the bit error rate. The bit error rate is we count how many errors made. So when the transmitted symbol doesn't match the received symbol, then an error is made. We divide that by the number of bits transmitted. And this is the bit error rate. Here we have the same thing shown pictorially. So we've got user 1, 2 and K, all occupying the same narrow bit band bandwidth from 0 to BM. These are all in the frequency domain, or omega. Then we spread the signals, and they're shown on top of each other here, just so that we can see them all. And we also have the noise here, or sigma squared, which is N0B A, and then we despread our actual signal, with code 1, and then we have the approximate, so we've got the approximation sign here, message signal from message 1 plus the noise here, and then we've got the interference from user 2 to user K. And obviously this goes on to a much higher bandwidth, which is twice BA, but we can use filters to only take into account the signal that we're interested in. So, high signal to noise ratio of the message. Here we have the original equation that we have defined in terms of signal to noise ratio of the message and the spreading gain. So if we have the same equation, then the multiple axis interference now is given by the number of users that we have, which is K, take away 1. The reason it's take away 1 is because we're one of the users and we can't interfere with ourselves. So K minus 1 times P over G plus sigma squared, all divided by P, is the signal to noise ratio at the output. So if we then put that into the equation, then we're saying we've got a very high signal to noise ratio of our message. So if we're tending to infinity here, then infinity divided by infinity are going to cancel. So we will have G infinity over 1 is going to be infinity, plus K minus 1 over G. Invert this, G over K minus 1. K is approximately equal to K minus 1. So K equals G over signal to noise ratio at the output. So what we're trying to say is in CDMA there is no reuse factor, or the reuse factor is 1. If the codes are orthogonal or semi-orthogonal, then we can use the codes, or there is no reuse factor. The only thing that limits us is the multiple access interference and the fact that the difference in power levels, because if P is not the same for all users, as I've shown before with the near far problem, then the multiple access interference will be affected, and obviously there will be a degraded performance. Compare this to the reuse factor for frequency and time division multiple access when we've got 1 in 7. We've got 1 in 7 here because we have a cell size or a cluster of 7 cells. Then the channels that are used in cell A are, if we have 100 channels, I should have used a better number, but we've got 7 channels. So in here we have 100 over 7 channels can be used in each cell. We don't want to overlap these cells, so the channels, say the first channel will be used in channel A, the second channel in B, third C, fourth D, fifth E, sixth F, seventh G, eighth back in channel 1, the ninth in B, so on and so forth, because we don't want the channels to be next to each other, because then they're going to interfere with each other more. So the distance between where a channel is used and it's used once and whether it's used in a different place is this distance from the centre of cell A to another cell A, and those distances should be equal. We will go through this in a tutorial. So, multi-user channel capacity. If we have n multi-users, basically what we're saying is, because it's CDMA, the capacity is equal to the sum of all the powers and all the receivers, receiver 1, receiver 2, receiver 3, up to receiver M. And what we're saying is, because the channel reuse ratio is 1, then we have every user can use the whole channel. So the channel capacity is at a maximum, so it's not limited by the number of users. This has no effect. So we just have C, channel capacity is log to the base 2, 1 plus P over N.